Today we're going to talk about a pretty important topic. Well, two important topics, but the first one is more important. Integral test. Okay, so the reason we need this test is because we really have no effective ways of determining what a sum equals. We can take a computer, we can add these things up, but we're not going to have this great coincidence where Riemann sums end up being an integral, right? We really have no way of figuring out a closed form for arbitrary sums. Thereby, we're usually limited to approximating these sums. And whenever we approximate something, we need to establish a couple important things, right? Well, one important thing maybe. Is the estimate that we're giving underestimating the sum or overestimating the sum? And normally we want to find both an underestimate and an overestimate. So we can say, listen, I can't give you the exact sum, but I can give you an interval where you would expect to find the exact sum. And by shrinking the interval, we can sort of improve our approximation. So what I want to start with today is something called the harmonic series. Harmonic series. And that's a sum of this form. It's the sum k equals 1 to infinity of 1 over k, which is 1 over 1, 1/2, a third. Is this the geometric series? Well, we learned what geometric series were yesterday. What is a geometric series? Yeah, r to some exponent where r is a fraction. Is this r to some exponent with... No. So is it a geometric series? So can we use the geometric sum formula? So don't be tempted to. I want to establish if this sum is convergent or divergent. Who has a guess? I told you like yesterday. Yeah.
Divergent.
Yeah, this is divergent, despite the fact that the numbers are decreasing. So you can see that the numbers are trending to 0. Yeah? But this sum is nonetheless going to sum to infinity. Right? So this is the harmonic series is usually an example you have to keep in mind as the most typical example of a series that has sum-ins that go to 0, but that nonetheless diverges. How can we argue that this is divergent? No? That's what we're going to resolve today. So the first thing I want to realize, I want to convert these series into the geometric space, but they're not functions, so this is a problem. Is there a way that I can represent the sum of a series as the area under some type of plot? Well, let's consider this, right? If I space these out by 1, right, so this is 1, this is 2, this is 3, this is 4, this is 5, 6, 7, 8, so on. And if the delta here is a unit, what can I do? Well, I can make a bar chart. Something like this. Where did I start in here? Yeah, let me start here. So I can do this. And if this point here is A1, then this bar has area what?
A1 times 1, which is
A1. Right? I can sort of repeat this. I can say that this is A2, this is A3, A4, and so on. Okay? So more specifically, if this is at 1 over 1, if this is at 1 over 2, geez, my scaling is totally off, but you can fix it. What I'm trying to, do you sort of appreciate that this area is going to give us the area of the sum? Right? That I can set up a sort of bar chart that will have area equivalent to the sum. Okay, great. So if you allow me to do this, notice what I can do then. If I know these points, okay, I can run a function through this. Specifically, the function for the harmonic series is going to be what? F of x is equal to 1 over x. Everyone see that? is the area under 1 over x less than or bigger than the area under the bars? Less, right? Because we're missing all of this, all of this, all of this, all of this. But what then have we observed? We observed that the integral from 1 to infinity of 1 over x dx is in fact less than the sum from k equals 1 to infinity of 1 over k by this sort of geometric argument. Does that make sense? Tell me if it doesn't, because the whole lecture is dependent on understanding this setup. And so everyone understands how I can take a series like this and represent it as the area of bars? Yes? Everyone understands how the height of the bars are given by the individual summons? Then we understand that we can actually just run a function through it, 1 over x. Okay, so let's resolve this then. What does this equal? Well, this is the limit as b, maybe I'll just put this implies that the limit of b goes to infinity from 1 to b of 1 over x dx. What is this equal to? Well, this is the limit of b goes to infinity of ln x from 1 to b, which is infinity. I hope you will let me skip the intermediate terms, right? So ln b minus ln 1, which is 0. Okay, so this is bigger than or equal to infinity. What does that mean about the harmonic series? Yeah, the area, or this, which is equivalent to the area of a bar chart, has greater area than this integral, which diverges. Thereby, this has to diverge. Does everyone follow that argument? Look, really, ask me questions if you don't, because this is something called the integral test, and that's all we're going to talk about today.
So when the sum approaches 0...
What sum?
Like originally, right?
No, the sum isn't approaching 0. We have to be careful how we speak about it. The sum is approaching infinity. The summands, the terms themselves are approaching 0.
So we know that it can either converge or diverge, and this is how we check?
Well, if the sums approach 0, that's the necessary condition for convergence, right? If we're looking at a sum and the summands they diverge, we can immediately conclude that the series is divergent. So the first thing we check is that the summands go to 0. But the problem is we'll usually give you sums whose summands go to 0. And then we have to use other tricks. One of the tricks is the integral test. It's not the only trick. We're going to learn some other ones after this one. But we need some way of utilizing calculus to talk about these problems. Like, these sums aren't problems of calculus. This is an algebraic type of statement, right? We don't, if you remove the real line, everything we've talked about doesn't exist, right? We don't have limits, continuity, differentiation, right? So this, we always have to attempt to take the problem and drag it into calculus so we can utilize the tools that we've built. And specifically, the tool that we need to use are these divergent or these indefinite integrals. Yeah?
So how would the test show that it's convergent if it was in infinity?
Okay, so anyone have any ideas how we could use the same argument to show something is convergent?
So when you would use, like, you did the integral.
Well, you skipped a step. First, we'd have to show that we'd have to pick these endpoints, right? Because we want the area of this sum to be less than that of the integral. And then we have to hope that the integral integrates to something convergent. This is naturally the next thing I'm going to talk about. So why don't we move on? All right, so just look at that. I'm going to draw more pictures. There's a little bit more explanation in the notes. So where are my pictures? What? I had some very nice pictures drawn, and they have disappeared. All right, well, let's try another one. Okay, so what have we determined? This is pretty important. sum 1 over n is divergent. Okay. This is a very important example to keep in your head. The next thing we're going to have to do is something called the comparison test, and we're going to need a sort of box of examples to compare to. Here's the new question. What about this one? Sum k equals 1 over k squared. Almost the same thing as we were just doing, but I increased the bottom. So first of all, are the individual summons bigger or smaller? We're dividing by more, so the individual summons are smaller, so we expect the sum itself to be smaller. So maybe this one is convergent, or maybe it's divergent. Being smaller than infinity doesn't really tell you much if you can be infinity. Any guesses?
Convergent.
You say convergent? All right, let's see. Right, because it's like, I sort of knew that this was divergent first. That's why I ended up picking those endpoints. You are correct. I'm going to tell you that you're correct, that this is convergent. But I just want you to get the idea that you're supposed to identify this ahead of time. Like sometimes, if you guessed that this was divergent and things don't, convergent, sorry. If you had guessed that this was divergent and were wrong, you do a lot of work which wouldn't work. And then you'd have to sort of ask yourself, okay, maybe it's convergent. Right? But usually the only way we have to, like we usually have to run to a computer and ask the computer to do the sum to like 10 million. And sort of see what the behavior is like. Right? There is a notion of mathematical experimentation. Right? I used to work in a lab called the Center for Experimental and Constructional Mathematics. And that was one of the things that we were interested in. Right? The number theorists would say, we don't know what this limits to. Can you use a computer? Can you try to find out the limit to as much as the computer will allow? Okay, so we have 1 over k squared. I want to bar chartify this sum. All right, so again, I'm just going to take unit intervals. So the first thing I want is a bar. This is not to scale. This bar is going to go through 1, right? Because the first sum here is 1. So this is the bar for A1. The bar for A2 is going to be 1/4. So actually, this is like tapering off pretty fast. Half, quarter. Yeah, I'm not going to draw this to scale. But suffice it to say, these things are going down. If I drew it to scale everything, it would disappear so quickly. A3 and so on. So A4, A5. Actually, I'm going to move those labels underneath. All right, so the point here is that the area of each of these bars corresponds to one summand, right? This is the area of 1, 1/4, an 1/8, 16th, 32nd. Okay, so you have hypothesized that this is convergent. Okay, so this means I have to find a convergent integral which has more area than this, and then argue that we're bounding from above this area. So what I'm going to do is going to run. Okay, I have to run an integral through here. And you can see that the area under this curve is what? More or less than the area? More, right? Because we're missing, this is 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 missing, and so on. Which means that the integral from 1 to infinity, right? So what's this curve? Right? Yeah, 1 over x squared. So this curve is given by 1 over x squared. It's usually just the summand itself, right? Expressed as a function. Okay, so I have 1 to infinity of 1 over x squared dx. This is going to be greater than the area of the sum from k equals 1 to infinity of 1 over k squared. So let's work this out. This means we have 1 to infinity of 1 over x squared dx is equal to the limit of b goes to infinity of, what's the integral of 1 over x squared? I believe that's minus 1 over x from, 1 to b. So what do we get? We get 0 minus minus 1. This should work out to 1. Let me just confirm that. No, oh no, it works out to 1. Why do I have 2 in my notes? Have I screwed something up? Yeah, negative 1 over x. Yeah, I don't know. I wrote a 2 in here, but it doesn't really matter. In any case, this is, so the 2 in my notes is wrong. I got a 1 here. But the point is, this is 1. Right? That's what we just computed it to be, the integral. And we know that the integral contains more area than the area of the bar chart, which is equivalent to the value of the series. So thereby the value of this series, well, we also need that this is positive, but that's very easy to establish. None of these terms are negative. So we know that this series is stuck in between 0 and 1, so that has to be convergent. Make sense?
It has to be convergent because it's stuck.
It's like just the opposite of that, but.
Yeah, isn't it? Can I just say because it's greater than, then it's convergent, but then up there is because it's less than, then it's divergent?
Well, it's less than infinity,
Yeah, less than.
which means it's finite, which means it's convergent. Wait, did I? No, it's greater than infinity,
Yeah,
which means it's divergent.
Yeah.
Yeah. This is less than something that's finite, which means you have to be finite.
Yeah.
But if you chose the left endpoints, would it still be 1 over x squared? Like,
No, because you'd have an under approximation of the
But like,
of the
since
area.
you chose the right endpoints, isn't the function like shifted? Or is that?
Well, but then you could
actually
just like
not-
shift the picture left and right then if you want. I can like move all these bars back by 1. You can always set it up so that it works.
Okay.
Right?
Okay, so how do I know when to use what approximation?
Well, you tell me, right? Well, this is obvious, right? We have under approximations or over approximations. If we over approximate something, right, that means that the area is going to be less than the area so in that case that's the convergent case. It does, you show nothing by showing something's less than infinity.
Yeah. Wait,
Right.
What if you just predict wrong?
yeah, like,
That's what the whole premise to this question is that you may predict wrong.
And then how do you fix that?
Nothing would work,
what?
right?
Oh, it wouldn't.
You would end up getting something like this sum is less than infinity. Less than or equal to infinity. That doesn't say anything.
I thought that was divergent, and I did the under approximation. Like I did it from the left.
Let's try a few more examples, right? Maybe that will flesh out, but yeah.
So if it was any finite number, it'd be convergent, right? Anything beyond infinity.
Yeah, anything finite will suffice, right? I'm saying the area trapped under this curve is finite. Thereby, the area of the bars have to be finite. It's not a very sophisticated argument. Okay, well, stare at this. And then I'll actually talk about the integral test, right? So you should note then that sum 1 over n squared converges. Right? We seem to have found some type of breakpoint in those sums. But again, I think your question is more along the lines of how do I know how to answer the question correctly before I start?
Yes.
And my answer to this is there is no, you gotta try. I give you a bunch of tools, you may fail. Right? You fail with one of the tools, you move on to the next one. But like, do you know how easy science would be if we could take these sums? Right? I'm not trying to torture you. This is just this is the best current technology we have for dealing with these things. An expected value, for example. If you had a very sophisticated experiment and you needed to do an expected value, and suppose like your sample space was in like the billions, right? You're gonna have difficulty finding that expected value for a variety of reasons. So you need to use these type of systems in order to compute anything. Right? In the real world, like we're not going to be able to integrate stuff. Right? So this is probably one of the most important topics, to be totally honest with you, for statistics and other type of stuff. Yeah, that's kind of cruelty of this course, is that we teach you all of these methods, which like never work. Like 5% of the time they will work. 95% of the time what we actually need are just numerical approximations. Okay, so I'm going to tell you what the integral test is. That's the integral test essentially. But I'll write it down. You just need some practice, as usual. So if we let an be a sequence, positive sequence, be a real positive, which means none of these can be a negative sequence. And suppose we have a function f of x, which is equal to an for, well, x equals 0, 1, 2, and so on. Right, it's basically saying the function itself just passes through all of the points as I drew them up there. Then, provided f is continuous, differentiable, and integrable, it'd be pretty silly for us to pick an integral that we can't integrate for this purpose. So make sure to choose one that you can integrate. And then, whoops. Then this sum and this integral converge and diverge together. So you know this question you had about the endpoints?
Yeah.
Turns out in the limit it doesn't matter.
Yeah. 'Cause
Yeah.
you take the-
Because there's just so many of them, it cancels. So that's why I didn't really want to talk about it too much. So essentially, if you can just find a function that like passes through all of these points, and you can integrate it, then this indefinite integral is going to tell you, why is this an n? Oh, this should be an n. This is just a technical thing where the sum can behave really dumb at the beginning and then sort of stabilize into something nice. So this is like an eventually clause. But for you guys, this will always be a 0 or a 1. But you can start anywhere ahead of time. Okay, so you need to be able to find an integral which bounds or doesn't even really bound, that just goes through all of the points that your series is going through. And then instead of sort of messing around with the summation, you can mess around with an integral. And we have way more techniques for dealing with integrals than we do series. All right, so you're going to need a bunch of practice with this.
Do we have to explain that, just like the mean value theorem and the rest of the series?
If you use the piece of technology, you have to state that you're doing so. Right? If you're saying like this integral converges and therefore the series converges, you have to say something like because of the integral test.
Oh, I don't have to explain that, just right because of the integrals.
Well, yeah, we're not going to ask you to rededuce theorems, right? That's the whole point of these classes. We do it once, you learn it, but then you sort of have to just be aware. Like maybe I don't even care that you say integral test. Like maybe try saying integral test is the best thing, but if you blank on the test on your exam, say by a theorem or something like that. Just so you're indicating that you're like, well, I know this isn't sort of obviously consequent. Like we needed to develop a framework for saying this. So that's better than just pretending, right? Or just put by theorem blank, right? And maybe I'll throw you some marks. Okay. So I want you to work this one out at home. It's a little bit tougher. For what p does the so-called p series converge and diverge? The p series is this. One over n to the p. Right? So if the p series for p equals 1 is called the harmonic series. That's a special case. And you already know that it's divergent. P equals 2, we did that as well, didn't we?
Yes.
And we found that was what? Convergent. So you should find that for p less than or equal to 1, greater than or equal to 0, you're divergent. Can we? Yeah, 0's fine. And for p greater than 1, it's convergent. Okay, and p is a real number here, not an integer. Right? So you can really do like 1 over n to the like square root of n. And you should be able to identify that as being divergent. All right, so the lecture we're going to do after this one, it's very important that we have a collection of examples, like which converge, which diverge, because we got to use them to like show the convergence, divergence behavior of other things. Okay, so try this one. It'll be tough-ish. So you got to solve an integral with a p in it, and then you're going to have a condition over that p. Okay, so let's try one exercise right now, which you can try. Does sum k equal 1 to infinity 1 over k squared plus 1, does this converge or diverge? Is it a p-series? No. So don't be tempted to use that. Okay, so here's the thing. All you have to do is integrate this. And as soon as you integrate it, it's going to tell you if it's convergent or divergent. Because we no longer care about like the endpoints. So all you got to do is integrate 1 over k squared plus 1. Or 1 over x squared plus 1.
Do you think we use the other method we learned, the geometric series? Like it would be 1 over k to the power.
Is this a geometric series? So no.
Wait,
Can we just split it apart? 1 over k. Oh no, the plus 1
Can you
is in the
trig?
denominator.
Like trig substitution?
Guys, what's the integral of 1 over 1 plus x squared? Arctan.
Oh.
Please don't forget all the basic stuff that we
I can
learned.
do that.
Huh?
I can do that technically with the triangle anyway.
Yeah, you could do it from first principles. Well, I just gave you the answer. Okay, so this is, we basically say, notice f of x equals 1 over x squared plus 1, right, has the property, right, that f of 1 is equal to a1, f of 2 is equal to a2, and so on, with ak, like this sum in here. And so basically, like we have a function which satisfies the property, or the preconditions to use the integral test. So if I integrate this now, we know that integral from 1 to infinity of 1 over 1 plus x squared dx is equal to limit of b goes to infinity of arctan 1 to b. So what's arctan at positive infinity? Pi half, yeah. Remember, it looks something like this. So you get pi over 2. And what's arctan of 1? Pi quarter. So you can minus a pi quarter, which ends up being pi quarter. Brush up on the trig, everyone. Okay, so we've determined that this integral integrates to pi quarters, which is convergent. So by the integral test, sum k equals 1 to infinity of 1 over k squared plus 1 is convergent as well. Now, the thing that you have to understand and appreciate, pi quarter is not the value of the sum. Right? This is the value of the integral. It is not the value of this. Right? So all it says is that this value is bounded somehow by pi quarter. But it's not telling us what it is. This is only giving us information about divergence convergence.
So why'd you say all you have to do is take the integral?
Yeah, to determine convergence divergence. That's still true. But like there are no, like I have no technique that I can give you to tell you what this is. Well, maybe this one because it's it's a rational polynomial. But generally speaking, there is no technique for telling you what the closed form of a sum is. In fact, it's usually impossible, just like integrals. Right? So like now we're just trying to do anything else. Like, okay, we can't get the exact sum. Can we at least determine if it's convergent or divergent, right? Because if it's a divergent sum, that's kind of degenerate. We can't use infinities in math. That just explodes everything. Right? So one of the first things we usually need to establish when working with a sum is, okay, is this even convergent? Because there's no point even talking about this unless this stabilizes to something. And that stabilization may not happen a computer may not detect it. I can give you examples of sums where you can take a computer, calculate the first 100 billion sums, and it seems like it's stabilizing. But it just approaches infinity very, 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 very slowly. So this is tough math. Right? I don't know why we end with this, but this is pretty already serious math. Okay, so, all right. Well, I'll do a different exercise at home. Huh? That's it, yeah. That's it. Right, so the integral test of it essentially boils down to you taking an integral. But that's the easier part of the integral test. Now I'm going to show you something harder.
Wait, so how is it bounded again? In what way is it bounded?
Well, this one, again, it doesn't matter that it's up or down. It doesn't, like, we can always shift the index, but in this case, this would be bounded by above. Right, we're saying that the area of the sum is less than that bounded by the area which converges. But it just happens that all we have to do is shift all of the bars left one or right one. Right? The integral stays the same. We just have to push left or right an endpoint. Okay, a couple exercises for you. Do the following diverge or converge? Sum n equals 1 to infinity, n e minus n squared. Sum n equal 1 to infinity, 1 over 2 ln n. So those are a couple to try. Let me explain. I'm the professor, right? Okay. So give these a try. Okay, so now we're going to pivot into a different topic, but still on integration test. I'm going to give you a practical question, and then we're going to try to resolve it over the course of the, I don't know, maybe the next 20 minutes. So I'm going to write the question first, which is a little bit out of order from my notes. Where the hell did I put it? Aha. Okay. Example. So let's return to this guy. Let S, I should put a space there. Okay, so let S equal the sum from k equals 1 to infinity of 1 over k squared. This is a p-series. You may have noticed I didn't give you a way of actually determining what the value of this is. I don't know what the value of this is. So, suppose you had a job, and I don't know, you're a scientist, and you determine that you have some sum, and you don't know if it converges or diverges. Okay, no. You do know that it converges. We know that this is convergent. But your boss says, look, we actually need to use this value somehow. Okay, so can you go and calculate it? But I need you to calculate it in such a way that we're sure that the sum that you calculate is only off by maybe 0.1. That's a reasonable thing to say, right? They're saying, give me an approximation to this type of specificity. And I'm telling you, we can actually work that out. So find, we're going to call this, find an estimate. I'm going to call that S hat, right, of the exact sum, so that the precise sum minus your estimate is less than 1 over 100. Right? This is a statement about find me an estimate that's close enough. Right? I want you to be within 0.01 of the true value. How do you think we could do this? Now we got to sort of think like scientists and computer scientists rather than mathematicians. Well, does anyone have any idea how you could try this?
Can we use, you know how if it was just n, we use n minus 1 over 2?
Yes.
And we know if it's squared, it's 2, and then bracket n minus 1 times. You see what I'm talking? You still
Nope.
remember those formulas?
We have closed forms for polynomials, essentially. We know how like the sum of n squared goes. We don't know how the sum of their reciprocals go.
We cannot manipulate it.
Huh?
We cannot manipulate it.
That's what I'm trying to tell you, is that we don't have closed forms for these things. Right? Sums are hard, right? It's easy to write down a sum. Add up all of these things to infinity. Then it's amazing how hard it is to actually determine what the exact sum is, right? Mathematics gives you great power to write down stuff, which is like, it seems really simple when you write it down, but it's very complicated when you try to solve it. Okay, so this is our motivation for something we're going to talk about called error estimation. Okay, and this is very important in like applied statistics and stuff like that, where they aren't able to take integrals and do precise sums. So they always just have to say, well, we'll give our best approximation to this. So we need some language to talk about this. So I'm going to say denote by Rn, which is going to be, so this is the exact sum. This is the nth partial sum, right? The sum of the first n terms, or n plus 1 if we start by 0, which means what's left is this. An plus 1 plus an plus 2, and so on. Right? So this is something called the remainder. Because the idea is that you get a computer to compute a partial sum to like 1,000,000 or something like that. And then these are all the terms that you didn't bother adding. And the terms that you didn't bother adding, we can consider to be the error, right? That's what you've missed. So now let's see if we can try and figure out how much error we have when we've computed a partial sum with n terms. So now I have to be very careful. I have to draw some pictures. Okay, so first suppose f of x is equal to an for x, all the index variables, right? So we truly go through all the points. I'm going to draw two graphs. We have to now go back to this notion of overestimating and underestimating, because we're really talking about the area now. So I got to draw two graphs, and I got to be careful. I always screw these up. This is very nuanced. Okay. So basically we want to look again at the two type of estimates that we can take on our bar chart. So this is n plus 1, n plus 2, n plus 3, n plus 4. Here, what do I got? n plus 1. Plus 2, plus 3, and plus 4, plus 5. Okay, so this is going to be the integral that we're going to take to try to argue that the sum is either bounded below or above it. So one of the type of estimates we can take would do this. It would go through here, like this. Okay, where this is the a(n plus 1 term. This is the a(n)th plus second term, a(n)th plus third. And when I write this, I mean the area of this bar is equivalent to that summand. Now, in this example, is this extra or missing? Huh? Missing, okay? So this is missing area. So is it an underestimate or an overestimate?
Underestimate.
All right, this is an underestimate. Where can I write this? Okay, so I'm going to call this star, and this is going to be called star star. Okay, so for star, star tells us that the integral from n plus 1 to infinity of fx d of x is less than the an plus 1 plus an plus 2 and so on, v, which is just the remainder term. Right, so this is where our remainder starts. Right, so if we use we can take an integral and we can actually figure out how much we've missed in terms of the remainder, in terms of the stuff that we didn't bother. Like we're basically trying to, this is now going to say how much we're off by, right, in the uppercase. If we look at the lowercase, something like this. I always draw it wrong. Yeah, I almost did it again. Okay. This box here is going to be for an plus 1. This box here is going to be for an plus 2, and so on. The difference between that and the bar is this extra area or missing area? Extra area. Okay, so this is extra area. Which means that this is a overestimate. Okay? Right, so I'm basically just looking at the sum, starting where we stopped adding in the partial sum. So double star. Right, so since this is extra area, overestimate, we have that the integral from n to infinity of f of x d of x is bigger than the remainder. All right, so this Rn is the terms that we didn't bother adding up. Right, so now I want to see how big the stuff that I skipped can be and how small the stuff that I skipped can be. Right, just to sort of say that, well, I get this partial sum, and I want to say what my plus minus is, essentially. Okay, so we know that the remainder is bounded above and bounded below by those intervals. You may have to go home and think, well, you definitely have to go home and think about this again. Because I am kind of rushing. There's 2 topics we have to do today. What time is it? Huh? 12, okay. Okay, so I'm going to give you a proposition, which basically is a codification of what I wrote up there. And so suppose you have a sum. You have a sum of an. You've calculated Sn truly with a computer or something, like actually computed. Then if Rn is the real value minus S of n, well, I guess I should write it like this. Sum A of n minus the partial sum. Then I can actually tell you that the remainder is bounded above and below by 2 integrals. It's bounded above by the integral from n goes to infinity of fx d of x. That would be the, which one, left hand or right hand? Left hand. Or was it left or right? I'm smaller than, so it's the left one. It's this one. And then it's bounded below by n plus 1 to infinity of fx d of x. Right, so I know how much I'm off by. This is telling me how much I'm off by. And it's saying you're off by at most this and at least this. All right? I can write this in a different way, which would probably resonate better with us. Or, equivalently, let's write it like this. I could say Rn is in this interval. Oh, not Rn. It's even better than that. Sum A of n right? The true sum, the thing that we would want ideally, is in this interval, right? It's your partial sum, the thing that you have actually computed with a calculator or by hand, plus this integral, right, the left-hand side, n plus 1 to infinity f of x d of x, and Sn plus integral n goes to infinity fx d of x. Now, and if you didn't really understand anything that happens up there, just try to appreciate what this proposition is saying then. It's saying, look, we don't know what this is, this symbolic, or this exact sum. We do know these partial sums for arbitrary, like for as long as you're willing to compute something. You can compute Sn, right? 100 terms, let's say. So this is telling you if you compute 100 terms of your partial sum, that the true sum, the exact sum, is going to be in this interval. And let's draw the interval. The interval is going to be, okay, but I want to return now to the example where we're talking about. Okay, so let's recall our early example. Recall, we were trying to figure out this, right? And we're trying to find an approximation, S hat, such that, right, the difference between this guy and our approximation is less than 1 over 100. So I'm going to kind of ask a backwards question here just because it's fun. Well, because this, we can work out how many terms we have to compute for the partial sum in order to be within 1/100. Right? So let's first develop what we should guess and then see how that guess, how accurate that guess is. So remember, we can always trap the exact sum into this region. Right? And we hope that these things are very close. And in fact, this interval is going to shrink as you increase n. All right, so it's going to make more sense if we use an actual example. So what function will go through, has the property that it goes through each point 1 over k squared? 1 over x squared, right? So first notice f over x is equal to 1 over x squared has the property, right, that f of 1 is equal to 1 over 1 squared. F of 2 is equal to 1 over 2 squared. And f of n is just equal to an in general, where an is that, oh, sorry, that should be an n. Or that could have been a k. Doesn't really matter. Okay, so what integrals do we need here, right? So suppose we've calculated, suppose we have some partial sum, okay? Then the next two things we would need are a couple integrals. We need the integrals n plus 1 to infinity of 1 over x squared dx. And this ends up evaluating to 1 over n plus 1. You can and should fill in the details at home. And we know that the other one, n to infinity of 1 over x squared dx, this works out to 1 over n. Stare at that. Make sure that that is correct. Huh?
So it's like 1 over k squared and then 1 over x squared and then 1 over n.
Well, no, the x is deliberate. The k wasn't.
Oh,
Shoot.
okay. So it is 1 over x squared and 1.
Yeah, n.
Okay.
Yeah, sorry, it's hard to keep some of those indexes straight. So a lot of the dollars I got were noticing indexes at the place. So the problem with those variables for like mathematicians, they're just like auxiliary, useless variables. So we don't really Yeah, a lot of mistakes can be found there. Okay, so I'm going to draw the number line now. And let's try and illustrate what it is we've deduced. Okay, so the exact sum that we want actually is this. And what our proposition has said is that we found a region where this S is trapped. So if this is the number line, the real number line, we know that the true value has to lie somewhere in between Sn plus that integral, which is 1 over n plus 1, and this partial sum 1 over n. That's just what the proposition is told. This is just this interval drawn as a number line. So we know that S, the true value, is somewhere in here. Right, so notice, if you gave me an n like 100, I could compute S of 100, and then this would be 1 over 101, and that would be S of 100 plus 1 over 100. So this would really be a tiny interval. Okay, I'm telling you that we've managed to trap the real exact sum in between these 2 points. We now have to pick an estimate. Where should I choose my estimate in this interval? There's not really a correct answer here, right? There are some answers that are better than others, but none will be incorrect in the end. Well, think about what the original question was. We want to find a sum which minimizes error to the true value. Okay, so let's think about this. If the true value was here on the boundary, and we guessed here, that would be the worst case scenario. The best case scenario is if we actually guess correctly. On average, the minimum error will be given if we guess the middle. Guessing in the middle is the best case here, because the worst case then becomes half the distance rather than the whole distance. Does that make sense? Okay, so notice I've already said something, right? What is the maximum difference between the exact sum and our guess?
1 over 100?
Well, it's this distance. That's this distance. Half the length of this interval. Yeah? Okay, so we know that the true value of the sum minus our guess is going to be half of that distance. So it's 1/2 the bigger one, Sn plus 1 over n minus Sn plus 1 over n plus 1, which ends up being what? So these Sn's cancel. If you combine these, you're going to get n plus 1 minus n. So you're going to get 1 over 2 n plus 1. Okay, so this is the maximum error. Okay, so if we guess here, the worst error we can have is if the true sum lies there or there. If it's anywhere else, it's going to be less than that. Okay, so, less than or equal to. It's going to be less than or equal to this, less than or equal to this. But what was our goal? What was the initial goal?
Wouldn't the negative sign apply to both the Sn and the 1 over n plus 1? Because we're subtracting that whole term.
Oh yeah, you're right. I still think it ends up, I think in my mind I did it right, but on paper it was wrong. Yeah. Thank you for that. Okay. What was our original goal? Here, right? This is the original goal. I guess I started writing this as S. Right? We're very close, aren't we? Pick me an n that will satisfy this. Well, I need to force this to be less than 1 over 100. So for what n will I get to be less than 1 over 100?
100?
I'm going to walk around the class once.
Wait, that's gonna be greater than.
For what n
Oh, it has to be
is that going to be smaller than a 1 over 100?
Any number that's less than 100?
No, it will be
Oh, no,
smaller.
less than 2
That's
times.
smaller.
So like square root of 10. Or I can just choose 10.
7 times 8 is 56. Twice that is more than 100. You can see that one.
Oh, you.
That's what I'm saying. That's what I'm saying. Well, a little bit.
6 times 7 is 12.
Okay, I just feel like I'm in it's whatever. The average. Maybe we should notice. We should notice the car.
Oh, okay, I was gonna just move it the other way. But yeah, okay. It does the same thing.
Did you guys actually answer that, or did you hear me say it? That's it. I think everyone's overcomplicating this a tad, right? Like, what happens if I put n equals 7 in here? Right, this is equal to 1 over 2 times 7 times 8 for n equals 7. Right, 2 times 7, so this is 56. Double that is 112. So 1 over 112. Yeah, so 1 over 112 is less than 1 over 100. Right? Okay, so if I make n equal 7, this will be within 1 over 100 of the true value. Okay, so all that's left to do now is actually to produce our estimation.
You could have picked any n, right? Any n that would have made it less than 1 over 100?
Exactly.
Okay, so 7 is just a random number.
No, 7 is the first number which gets us over this threshold.
Okay, so you want the minimum number that gets.
Ideally, I want it, well, this is a very constructed example where it's 7, but like, imagine you had a computer. There's a big difference between computing the first trillion and the first billion or first million, right? We are always searching for the minimum one that we can do. Okay? Especially if that will have like huge consequences when you're doing other type of science. Because you get to say, I'm going to compute with this value which is only off by this much. And then we can sort of estimate in the end how much our answer is going to be off by. Okay, so but for n equals 7, this will work. So let's actually deduce then what our value is. How can I actually, like, what is my s hat? Like, I need to write down an equation for s hat. How do I get it? It's here. Huh?
You want an exact number.
What is this value? Put on our thinking hats. There's many ways that I can express this. But it's the average of these 2 points. That's one way of doing it. Right? It's this plus half the distance. That's another way of doing it. Yeah. If we have 2 points on the number line, A and B, the point in the middle here is the average of A and B.
B minus A divided
B minus A divided by, yeah, in this case it's B minus A divided by 2. Okay. Does that make sense?
Yeah.
Okay. So in order to get this, I just have to average these 2 points to get s hat. Okay. So s hat is going to be the average of those 2 points, which is going to be 1/2. And I have to add them, right? So it's double Sn plus 1 over n plus 1 plus 1 over n. which is going to be Sn plus 2n plus 1 over 2n. Okay, so here's our estimate. Right? Here's the partial sum, and then here's like a little correction to that partial sum, which is going to help. So, what is then S7? Right, that's totally doable. S7. This is going to be 1 over 1 plus 1 over 4 plus 1/9 all the way up to 1 over 49th. And then S hat is going to be this number, S7, plus this adjustment, 2 times 7 plus 1 over 2 times 7. I put this through my computer, and I got 1.64. Right, that's what you'll get if you run this through a calculator. You're going to get a lot of extra digits, but be careful when you're using your calculator. I've given you no assurances about what those digits mean. Right, your calculator is going to give you endless approximations, but those, well, I hope you understand the difference between like sufficient and sufficient. Wait, what do you guys call it in science? You know, you talk about the accuracy versus precision versus significant digits. All of that sort of comes into play. But anyways, I also computed S, the partial sum, 10 to the power of 10. Can anyone say that number? Is that a number? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 100,000, million, a billion? Is 10 to the power of 10 a billion? Okay, so I computed the partial sum for the first 1 billion terms. And that ended up being 1.6457. So look, with 1 billion terms, with 7. And if you may not appreciate what we've done today, but this is really important. Right? We don't want to use a billion terms if we can get our approximation in 7. So statistics is very obsessed with these type of approximations because, again, they have no good ways of integrating over the distributions that they require. So they normally have to turn these integrals into sums, special Riemann sums. We didn't really do that much with Riemann sums because we went straight to integrals. But sometimes you're going to have to do a Riemann sum like this, right, and give error estimations. Okay, so that's where we're going to end this one. Yeah.
Find S hat though. Didn't you say we're going to subtract the bigger one from the smaller one?
I said I'm going to take the average of those two numbers. And that's what I did.
You added all the numbers divided
Divided by 2. That's the average of two numbers. Is the sum of the numbers divided by 2. That's why I was skeptical when you said b minus a over 2. That's half the distance.
Yes.
That's not actually the place on the number line. You have to add a back to that to reorient yourself. That's why I prefer to take the average. Okay, we can't take a break, but I am going to stop this before we start the new one. I need 5 minutes just to compose myself. So you guys got 5 minutes.